This is lecture 2, part 1, where we will continue from last time the perceptron learning and move on to logistic regression. So before I start machine learning, I want to talk about some administrative stuff again. So the first thing is I want everyone to give me feedback on my lectures, homework, and exams. And if you want to give anonymous feedback, you should do them on Socrative. Socrative is the app that we use for the quizzes. So if you go on the website and log into room CS540, you don't need to log in. You don't need to enter your name so that you know it's anonymous, and you can give me any feedback anytime. Okay, so if you see bugs or if you see mistakes in the homework or in the lecture examples and so on, I want you to report it on Piazza instead so that everyone else can see this. So everyone else can confirm they have the same bug and basically share the information. What I don't want is leaving comments on YouTube. The reason is I'm not going to look at comments on YouTube because many comments on YouTube are very offensive. So, well, if you want to leave something offensive, you can do it on YouTube, and I'm never going to look at it anyways. And if you have personal issues, you should email me directly. So, for example, if you have problems with your grade and homework, you should email me. But I think I said in the last lecture that you can submit homework late. So basically, you can submit it any time before the final. So if you are late by a few days or a few weeks, you don't need to email me. And lastly, if you have issues with me, for example, if I said something offensive to you or if I did something offensive to you, you can email the department chair. But maybe I don't know that it's offensive, so you should email me first. But if it's really a big problem, you should email the department chair. And yes, next I want to talk about a few feedbacks from last year. The most frequent one is I did too much math in this course. And that's kind of hard to fix because I don't want to skip those maths because this course, Introduction to AI, is trying to introduce you to the mathematics and the statistics behind some of the important machine learning algorithms. So I do not want to teach this course as a programming course or as a machine learning package course. So I'm going to still focus on the math and stat. But what I'm going to do differently this time is I'm going to record more videos on those math topics. So if you have taken Calculus 2 and Algebra, you can skip those videos, and I will separate them from the main lectures so that you can view them depending on whether you have taken courses on those topics. And the next thing is, some students said I spend too much time on math. Some people said I spend too little time on math. So again, I will separate them into separate videos so that you can choose which ones to view. And the next thing, I remember there are like 5 people said that they cannot understand my handwriting. So when I look at my note for lecture 1, I think that's actually a problem because it is hard to understand. So I don't know how to fix this problem. And actually, that's why I type up in the important things. So I have the typed up lecture slides so that the important things are typed. So hopefully it'll be good. And also I'm recording videos. So when I'm writing, I'm also saying the thing that I'm writing. So hopefully you can figure out what I wrote that way. Next, mistakes on slides. So as I said, you should report them on Piazza. And hopefully I fixed most of them last year already. So there shouldn't be many, hopefully. And last thing, more examples. And this year I am going to give more examples. And I'm going to use last year's quiz questions as examples this year. So indeed, you will get more examples. Okay, now let's get back to machine learning. So last time we talked about supervised learning, and the basic idea is we have the training data set, so we have a sample, and the training data set are the ones that are already labeled correctly. And for example, you have images of cats and dogs, and we represent the cats and dogs by some features, so a vector of numbers. So for example, the width and height, and so on. And given these already labeled training data, we want to find a function that best classifies these two classes. So we call this the fhat, the classifier. And last time we tried to find the best line that classifies the two classes. And then if we get a new image, so for example, we have a new image here, using the same line that we found, we can classify new images. And last time we introduced the idea of a perceptron learning algorithm. So basically, we have a bunch of points, and we have something like this. And we started with a guess. And here we are making two mistakes. And we try to somehow rotate this line so that it makes less mistakes. So for example, in order to fix this point, I just rotate it, for example, like this, so that the number of mistakes is 1. And then if we rotate again, then the number of mistakes will be 0. So it seems what we are trying to do is we are trying to minimize the number of mistakes by trying to find a function that does that. And this is indeed the framework that we're going to use. And let's make it more formal. So here, this expression means exactly the same thing. We're trying to find a function that minimizes the number of mistakes. But let's spend some time to read it. So here, this fxi is just the prediction made by the current classifier. And when they're not equal, it's 1. And when they are equal, it is 0. So basically means when the prediction is wrong, we count it as 1 mistake, and otherwise we count it as 0. And we are summing over all the training examples. So this sum means exactly the same thing as the number of mistakes. And the argmin here is basically finding the function that minimizes this. So if I just write minimum, then it's just the minimum number of mistakes. And if I write argmin, it means the function that makes the minimum number of mistakes. So that's the expression that we're going to use. And sometimes this function is called the loss function, and I also call it the cost function, and they all mean the same thing. And as I said, 0, 1 loss function, the loss function that we saw, basically just counts the number of mistakes. And there could be other loss functions. So one example would be the square loss. So if you actually look at this is y hat, this is y. There are only 4 possibilities. We can list all of them. In the first case, it's 0 minus 0 squared is 0. 1 minus 0 squared is 1. 0 minus 1 squared minus 1 squared is also 1. And this is also 0. So this is actually exactly the same as this indicator function, y hat I not equal to yi. So basically, for binary classification, where there are only 2 possible labels, they are the same thing. However, they are different if we allow like fractional numbers. So for example, if y, the actual value is 0.5, if your prediction is 0.6, then the loss is 0.01, 0.1 squared. And if you predict something like 5.5, then the loss becomes 5 squared 25. So this is small, this is large, so it's reasonable. However, if you use the 0.1 loss, then 0.6 is 1 unit loss. 5.5 is also 1 unit, so they look like the same, but they are completely different. One is very close, one is very far. So in general, we would prefer something like this instead of this, just counting the number of mistakes, because we don't know how large the mistake is. Okay, so there is another problem with this. Let me actually write this down again. The cost of f, this is our f hat. Suppose we have the data set with y and x, say x1, and we have these things in the training set. So if you have seen least square linear regression before, the square error loss is basically take the distance between the line and square them and add them up. So we want to find the line such that the sum of these squares is the smallest. However, just using this expression is not clear. That's what we're doing, right? So we're just trying to find a function that minimizes the cost. So in particular, we can have a function like this. I mean, a function that actually passes through the points, and the cost will be 0. And 0 is the least you can get. So this is probably one that minimizes the cost. However, the problem is it's not unique. We have something like this, right? Or you can go more crazy and have something like this. As long as they pass through all the points, the cost is 0. So this will return anything that does that. So there are lots of functions. So we do want to restrict the functions that we want to a smaller set. For example, we only want lines. Then it's more reasonable. And that smaller set is called, okay, I'm actually writing it on the wrong slide. But anyways, the smaller set is called the hypothesis space. So the new notation is here. We are only choosing functions from this smaller set called the hypothesis space in order to minimize the cost. So one example, as I said, some of you may have learned about this before, is the linear regression. It is basically we restrict our attention on the set of linear functions, and we just choose the coefficients. I think in statistics they are called beta coefficients, and here we're calling them the weights and the biases. And we restrict attention to finding these values that represent this function f hat by choosing it such that it minimizes this loss. And we're not going to spend a lot of time on linear regression in this course because in machine learning, we are more interested in classification problems than having arbitrary y value. So in machine learning, y is usually 0, 1, cats or dogs, or if there are 3 numbers like 0, 1, 2, they are not ordered in the correct way. Like 0 can be a cat and 1 can be a dog, and 2 maybe a fox or something like that. And so they cannot be ordered. So y being 0, 1, 2 is not the same as y being a continuous ordered variable. So we usually don't want linear regression. And this is what it's saying in this slide. And there is actually another problem. So if we just want to predict 0 and 1, maybe we can use linear regression and say that if it's larger than a half, it's 1, and it's smaller than a half, it's 0. So let me actually draw that. So now suppose y is just 0 and 1. So suppose, say, this is 0 and this is 1. This is our x1. So there are some cats. So suppose that x1 is size. And there are some dogs like this. And if we do linear regression, it will be a line something like this, and we say if it's above 0.5 is one class, if it's below it's another class. It seems to be classifying everything correctly, so there seems to be no problem with this. However, this is not right. So suppose we add some new data sets, for example, some huge dogs. They are still dogs, suppose. Then if we do the regression, the line will be something like this, right? Because the outliers will influence the line. So when you do the above below 0.5 thing, you will classify these two incorrectly. And why is this happening? This is happening is because if you use the original line, the green, now the red line, if you look at this cost, so this thing squared is the cost. This cost is large. But it shouldn't be, because it is classifying the thing correctly, right? So if you look at this above 0.5, this is classified as dog. So there shouldn't be a cost, but it is included as a huge cost. So if you go back to my previous slide, when the prediction is too large or too small, the prediction is correct, but the cost is large, so it's not actually the cost that we want. So that's why we do not want to use linear regression and basically use it in a way to represent probability or have a threshold on top of the linear regression. So we want to change that, and we will change it by just adding a function on top of this linear function. Why? Because we like this linear form. We can estimate the weights, because it's easier to estimate numbers than to just create completely new functions. So we want to keep this part, and we don't want it to be just the linear regression. What we're going to do is we add another function on top of it. So I think I mentioned this last lecture. It's called the activation function. So indeed, we talk about the LTU perceptron. This is just one type of the activation function, which is just the indicator function. And there are other ones. So I will continue with the sigmoid activation function in the next part of the lecture.